Welcome back as we continue with chapter 14, part D. On this part, we're going to begin talking about colligative properties. So let's define colligative properties. That's a good place to begin. So we're going to describe what a colligative property is, and we're going to explain the difference between the effects that non-electrolytes and electrolytes have on colligative properties. So let's begin with colligative properties. And you probably saw this in practice last week. How many times did you see on the news the trucks spreading a substance on the roads, the liquid substance, not the sand? So what they were doing was they were adding a substance that when the water falls, it will mix with the substance, creating a solution. So when the water falls from the sky, it will no longer be pure water once it mixes with this. So at that particular moment, we're going to have a solutions, and it's going to have properties, physical properties. So one of the physical properties of this solution with water is that it will no longer freeze at the same temperature of water, because you put something on it. Now the property is going to change, and it's going to freeze lower than 0 degrees Celsius. So a colligative property is a property of the solvent that is changed when you add a solute to it. So this solute could be an electrolyte, or it could be a non-electrolyte. So what would be an electrolyte? Sodium chloride. And if you add it to water, you're going to get sodium ion aqueous plus the chloride ion aqueous. So you have an electrolyte. So you got water with ions now. So what would be a non-electrolyte solution? Well, sugar, for example. Sugar dissolves in water, but does not create charges, does not create ions, right? So the fact that you just added something to the water is going to change its properties, and we call these colligative properties because they only depend on the type and amount of solute that you put on the solvent to create the solution. So let's see how these properties are affected. And let's begin with this. Let's talk about vapor pressure. So we know that the vapor pressure of a substance it changes based on temperature. But if you have a substance like, for example, water, right, which is a bunch of water molecules attracted by intermolecular forces, some of them, they're always moving, so some of them are going to escape, and they're going to become part of the gas phase, and they're going to continue moving, and they're going to put pressure on the surface. So that's what we call vapor pressure. The more molecules of water escape, the higher the vapor pressure, and they will tend to escape more when the temperature is higher. So it's a property, a physical property that depends on temperature. So at a given temperature, water always have the same vapor pressure. It doesn't matter how much water you have. So what about when we put something into that water? Now we're talking about colligative properties, because you put a solute on the water and it's going to affect these properties of the solvent, in this case water. Excuse me. So let's see this problem. The vapor pressure of a 1 molar ionic solution, so we have ions in the water, is different from the vapor pressure of a 1 molar non-ionic solution. So depending on the solute, the property is going to change. So the vapor pressure of the one with the ions is going to be different than the vapor pressure of the one with the non-ions. In both cases, the solute is non-volatile. This is telling me that the solute that I'm putting on that water is not gonna escape. is retained on the water. The molecule, the forces holding it there, they're too strong for them to move to escape. And the question is, which set of diagram best represents the difference between the two solutions? The difference are that they're different. They're not the same vapor pressure. And we know that the vapor pressure is given by the molecules on the gaseous phase, right? So we're talking about the molecules here, 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 there, and there. That's what's going to cause the vapor pressure. The first thing it tells us is that the vapor pressure is different, right? So let's do something. 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, and 7. The vapor pressure there is going to be the same. So that doesn't represent the situation because the vapor pressure is the same. So we're talking about a different vapor pressure. So the one that is ionic, on this case, is lower than the non-ionic. Can you see that? We got 4 on the ionic and 6 on the non-ionic. Does that make sense? Well, if I have something non-ionic, most likely something that cannot break into the ions. So what will not break into ion based on our experience? Not an ionic compound, because on this case we're saying that it dissolves. So it gotta be something that is a molecular compound, which most likely, unless it's polar, but most likely it's gonna be non-polar. So most likely it's only gonna have dispersion going for it. The ionic compound is producing ions, which is gonna create with the water an ion dipole interaction. Which one is stronger? Dispersion dipole or ion dipole? And we know it's ion dipole. So that force is going to be stronger. So it's going to hold those molecules of water together with the ions, and they're not going to be able to escape. So that means since the dispersion forces between the solute and the solvent are stronger, there's going to be less molecules on the vapor phase. So this will represent that. But this one too. So, okay, so we established that the vapor pressure on the ionic is going to be lower. Both of them are telling me that. So what's the difference? Well, if you notice, the ionic here have 1, 2, 3, 4, 5 ions, while the ionic on the other side have 1, 2, 3, 4, 5, more than 5. So since let's check the non-ionic. 1, 2, 3, 4, 5. Okay, so we're keeping constant the number of particles, and by keeping constant the number of particles, we can definitely say the ionic is going to be lower. On this one, we're not keeping it constant. We have more ionic, so that should be smaller anyway. But I would say if we're trying to portray this situation, we got to keep everything constant except the gas phase. So we know which one has more. So I would say this one gets the first prize. This one is a good second prize. And this one goes nowhere. That one doesn't show any difference. So what did we get out of this problem? Well, we get out that for us to understand this, we have to be thinking intermolecular forces. The stronger intermolecular forces between the solvent and the solute, the lower the vapor pressure is going to be, because less solvent molecules will escape. And why am I talking about solvent molecules? Because the problem told us that the solute is non-volatile. So the solute is not going to escape. That was established from the beginning. Is that the case always? No, it's not. On this case, it is. So we got to understand a little bit better vapor pressure and intermolecular forces changing the colligative properties. So once more, colligative properties is a property of the solvent that changes when you add a solute to it. So we're talking about the property of the solution. And it's going to be different from the property of the solvent by itself. Can we explain that the electrolytes are going to create a stronger intermolecular forces that are going to affect how easy they can escape? Yes, we can explain that also. And non-electrolytes by default are going to be weaker. What about a problem like this? Can we do calculations related to colligative properties? So can we calculate the vapor pressure of a solvent over a solution? Can we calculate the boiling point elevation? So the colligative properties, the way it's going to affect the boiling point is going to make it higher. So if you boil water at 100 degrees Celsius, when you put a solute into it, it's going to be above 100 degrees. The freezing point is going to be the opposite. If water freezes at 0 degrees Celsius, when you put a solute into it, it's going to freeze below 0 degrees Celsius. So it's a freezing point depression. So boiling point goes up, freezing point goes down when we're dealing with colligative properties of a homogeneous mixture, right, of a solution. And calculate the osmotic pressure. What we're going to do on this particular recording, we're just going to focus on the vapor pressure only. So we're going to save freezing point depression and osmotic pressure and boiling point elevation for the next recording. So let's talk about vapor pressure of the solvent over a solution. So the solvent is the one evaporating. And let's do it with this problem. Let's make sure we understand what we're doing. A beaker contains 100 milliliters of pure water. 100 milliliters of just water. A second beaker contains also 100 milliliters of seawater. What do we know about seawater? For those of you that have gone to the beach recently, it's salty. So most likely contains Na+, Cl negative, and other ions. So it contains ions. That's the point. The two beakers are left side by side, just like here, on a lab bench for 1 week. So after 1 week, the liquid level in both beakers have decreased. So we're going to have beaker 1, beaker 2, and the 100 milliliters went down in both of them. However, the level has decreased more in one of the beakers than in the other. So we got beakers A and B, and one of them is going to be lower than the other. Or we could be B and A. So we don't know which is which, right? Which one is the one with the lower level? Well, what do we know? Solvent by itself, dipole hydrogen bonding interaction, right? It's water with water. What about the solvent with the ions? Now we have ion dipole. Which one is stronger? Ion dipoles. Which one will allow the water to escape more? The water by itself. So if this is A and this is B, then this will be A and this will be B, because the level went down on the one that have the weaker forces holding it together. So just more re-emphasizing the importance of understanding intermolecular forces when trying to understand colligative properties. Moving on. So how can we calculate it? Well, we got the Raoults Law. It tells us that the pressure of the solution equals the mole fraction of the solvent, which is nothing more than the moles of the solvent over the moles of the solvent plus the moles of the solute. Remember, that's what mole fraction means. And we're talking about the one for the solvent on this case. So just the solvent. So the solvent goes on top, the solute goes at the bottom. So we understand this. What about this? What does that mean? That means that this is the pure solvent. So if water was by itself at a given temperature, what would be the pressure of water? That's the pure solvent. So the pressure caused by the solvent, remember, we're assuming that the solute is non-volatile, so the only thing on the gas phase is the solvent. The pressure of the solvent over the solution, that's what we're measuring. So if we have a glass of water with water, so water molecules, water molecules, and water molecules, but we also have a solute, right? Then the only thing that is escaping, because we're assuming that the solute is non-volatile, is going to be some molecules of water. And they're going to put pressure on the surface. So this is my pressure of the solvent over the solution. So that's what I'm measuring. So does it make sense that the more molecules of water I have, the more of them I will find there? Yeah, it makes sense. The more you have, the higher the possibility that they will escape, right? So that's why the mole fraction is important. So the higher the mole fraction, the more molecules of the solvent you have, so the higher the pressure should be. So if I multiply by a bigger number, the pressure should be higher. So remember, my main goal is that you care less about plugging numbers in there, but that you understand how the formula relates to the reality, to the chemical concept. So the higher the mole fraction, that means the bigger the number of moles of the solvent, so more of them will escape just based on probability, so the higher the pressure above the solution will be. The same with the pressure of the solvent. If the solvent by itself evaporates really easy, right? The higher this number goes, the higher the pressure will be because it evaporates really easy. So that's Raoults law. So let's see how we're going to use it. Oops. So let's see how we're going to use it. You see that I'm trying to hide some stuff in there. So let's keep it like that. So actually, let's go to the next page. So a problem like this. Calculate the vapor, which solution has the higher vapor pressure. And we know Raoults law. So the highest vapor pressure is referring to that number, the pressure of the solution. So what will make that number high? A bigger mole fraction of the solvent, so that the moles of the solvent is bigger than not the solvent. So the solvent is water, and water, so we care less about that. That's going to be the same for all three, so that's not going to help us compare. So what we're going to be focused on is this one here. The mole fraction is what's going to tell us which one is going to have the bigger pressure, because the pressure of the solvent is the same. This here is the same for all three, same solvent. So Which one will give us the higher pressure? The one with the higher mole fraction, right? So on this one, we have 20 grams of glucose. This one, you still have 20 grams, but the solute is gonna be different. So that's the amount of the solute. Remember, the mole fraction of the solvent equals the moles of the solvent over the moles of the solvent plus the moles of the solute, which means the bigger the moles of the solute, the smaller the mole fraction of the solvent is going to be, right? So if the denominator gets bigger, then my answer will be smaller. So the bigger the amount of solute is, the smaller the mole fraction of the solvent is going to be, which is going to make smaller the pressure of the solution. So we're looking for the one that will make the pressure the highest, right? So we want this to go up because we want this to go up. So we are looking for the one that gives us the least amount of solute. So think about that. Rewind, go forward until you get it. The smaller the amount of solute, the smaller the denominator, so the bigger the mole fraction of the solvent gets. The bigger the mole fraction of the solvent gets on the Raoults law, the bigger the pressure of the solution is going to be. So we're looking for the situation that gives us the smallest solute. So let's do that. We're looking for the smallest solute. So on the first two situations, which one gives us the smallest solute? Well, both of them are 20 grams, but this molecule, this one, we have a higher molar mass, which will make 20 divided by a higher molar mass, a smaller number of moles. So that one wins over that one so far. So far, this one is the one winning. What about the other one? Well, the other one is going to be 10 grams of potassium acetate, and we know the formula. The amount of water is the same, by the way, so no factors there. So we're going to have to see the moles of the solute, right? So you're going to take 10 grams and divide it by the molar mass of that. And that's going to give us so many moles. However, we're talking about potassium acetate, aqueous. You're going to dissolve it in water, right? Which means that aqueous plus the acetate aqueous. So if this happens to be 3 moles, you're going to have 3 moles of this and 3 moles of this. So the way we're going to do this problem is we already know that the first one is smaller than the next one. So that's gone. So you're going to take the 20 grams of sucrose and you're going to divide it by the molar mass of sucrose, and you're going to get a number. You're going to take the 10 grams of potassium acetate divided by the molar mass of potassium acetate, and you're gonna get a number, right? But this is gonna dissolve, so you're gonna multiply by 2 to provide the total numbers of moles of the solute. The one that give you the smaller number is gonna be the one that gives the highest vapor pressure. So you can do all those calculations on your own. I just want you to make sure that you understand the logic behind it. And then you get to do daily wear 14.10, 14.11, and notice on this one, you're giving a percent concentration. So remember how we learned earlier how to go from one type of concentration to another one. So you're gonna need to go from concentration in percentage to mole fraction. And then you get to do another one using the Raoults Law. And with that, you know what you need to practice in terms of colligative properties and vapor pressure using Raoults Law and mole fractions concepts. And that's as far as we're gonna go for now. So next time we meet, we will continue with colligative properties. We will do boiling point elevation, freezing point depression, and osmotic pressure. So until the next, see you later, take care.